In our last lesson, we proved Cantor's theorem, which tells us that for any set A is not equinumerous to the power set of A. Now, as a consequence of Cantor's theorem, we get that the power set of the positive integers is uncountable. But now, the real numbers are also uncountable from the result that we proved in our last lesson. So this raises the question, is the power set of the positive integers equinumerous to the real numbers? And so this is something that we are going to investigate on Wednesday. But in order to do so, we first need to discuss what is known as the Cantor-Schroeder-Bernstein theorem. And with that result, we will be able to prove that the power set of the positive integers is in fact equinumerous to the real numbers. Now, in the title for this video, I have gone ahead and dropped Schroeder's name, since Schroeder's proof was actually incorrect. And I've added Dedekind's name, since Dedekind was the first to prove this theorem. And so we will discuss the history when we get to the statement of the result. But now, moving forward, we have finite, denumerable, and uncountable sets. Finite sets, as examples, we have I sub n's for n being a natural number. Denumerable sets, we have the positive integers, rationals, Cartesian product of the integers with themselves. And we've investigated various enumerable sets as part of our study in 8.1 and 8.2. And more recently, we have now began our coverage of uncountable sets. But the thing about uncountable sets is that this is a massive collection, because to be uncountable is to not be countable. That is, finite or denumerable. And so we have the real numbers, we have the power set of the positive integers, we have 0, 1, but as a consequence of Cantor's theorem, we can take the power set of the real numbers, and that is going to provide us with another uncountable set. And similarly, we can take the power set of the positive integers. That will be uncountable. And in fact, by Wednesday's result, these two sets will be equinumerous, since the real numbers we will show are equinumerous to the power set of the positive integers. We also discussed in our historical coverage of set theory the continuum hypothesis. If A is a subset of the real numbers, then A is equinumerous to the natural numbers, or A is equinumerous to the real numbers. And if the continuum hypothesis were to hold true, which as we saw in the historical aspect, this is a result that is undecidable. It is one of those results that satisfies the incompleteness theorem of Gödel. We will never be able to prove or disprove the continuum hypothesis in our axiomatic system for set theory. But for the sake of argument, let us suppose that this were true. If the continuum hypothesis had been true, then we will have that there is no infinite set that is a subset of the real numbers whose cardinality is not that of the natural numbers. So in other words, it is not denumerable, and its cardinality is not that of the real numbers. Yet the set will be uncountable since it's not denumerable. And so the continuum hypothesis essentially gives us a way of, if it had been true, of counting infinities. Because we would have the cardinality of the naturals. We can label this as aleph naught. We can then take the real numbers and we can label this as aleph 1. And then we'll have the power set of the real numbers and we can label this as aleph 2. And we can continue in this process. And each time we get, by taking the power set of the previous, we get a larger set in the sense that its cardinality would be strictly larger than the previous one by Cantor's theorem. And so these are questions, this is one of the aspects of the continuum hypothesis that it would allow for us to order infinite sets via cardinal numbers. But unfortunately, the continuum hypothesis is undecidable, so this is not valid. We can still define aleph 1 to be the cardinality of the real numbers, but there is nothing to say that there is some cardinal number. There is some infinite set in between these whose cardinality is not aleph 1 or aleph 2, but is strictly in between. And that's, I'm being vague, but through the Cantor-Bernstein theorem, we will be able to specify what we mean by this vagueness of having a set of cardinality in between two infinite sets. But let us continue with this notion. Can we find a largest set? Is there a largest set? Well, we can do a recursion via what we just discussed. Let's go ahead and take A0 to be the positive integers. Then we take A1 to be the power set of the positive integers. And then we define recursively Aj to be the power set of A sub j minus 1 for j greater than or equal to 1. And so we have this recursive family of sets where if we plug in, say, j equals 1, we recover the definition for a sub 1, because now according to this recursion, we would have a sub 1 is equal to the power set of a sub 0, but a sub 0 is the positive integers. And so we have a1 is the power set of the positive integers. a2 would be the power set of the power set of the positive integers. But this gives us a family of sets, because now we have the family of sets where we can just take aj, where j is a natural number. And if we take the union of f, this gives us an uncountable set. And now, what it turns out that the union of these of the family of sets here, this is not equinumerous to aj for every single j. And so now we have a union, we have a set whose cardinality is strictly larger than each of these. But is that the largest set? Not quite, because then we can do the whole process once again. We can now go ahead and label b sub 0 to be the union of the family of sets. And we can take then b1 and take this to be the power set of b0. And then we go ahead, define recursively b sub j to be the power set of b sub j minus 1 for j greater than or equal to 1. And all of a sudden, we now have a new set, because we can take G to be the family of sets B sub J. J is a natural number, and we now have the union of G. That is going to be a set, and its cardinality will be strictly larger than each of the B sub J's, and in turn larger than the A sub J's. And so we can go ahead and continue this process ad infinitum, and so there is no largest set because of this procedure. As a consequence of this, we deduce that there are infinitely many sets such that their cardinalities are not the same, and via this construction. But now, I've been using this phrase, strictly larger. We haven't really defined strictly larger. We have an ordering between cardinal numbers, but now let's go ahead and make all of this precise via the following definition. So if A and B are sets, we will say that B dominates A, and write this notation here, which is reminiscent of less than or equal to, where now it's coming in like this, and a squiggle at the bottom. And so we have that B dominates A if there is a function from A to B that is 1 to 1. If B dominates A, and A is not equinumerous to B, then we say that B strictly dominates A. So when I was using the phrase strictly larger, I really meant that each AJ strictly dominates each of the A sub J's minus 1, minus 2, minus 3, all of the previous A sub J's. And similarly, the union of F strictly dominates each of the AJ's. and then the union of G strictly dominates the union of F. But now, what if we had that B dominates A? So in other words, we had this here, but we also have that A dominates B. From this, could we conclude that A is equinumerous to B? And this was what Cantor proposed in 1887 when he conjectured what we know today as the Cantor-Schroeder-Bernstein theorem, which tells us that if we have A and B are sets, and if B dominates A and A dominates B, then A and B are equinumerous sets. And so Cantor conjectured this in 1887, and with it he was able to give a new proof that the real numbers are equinumerous to Rn, where n is a positive integer. And so we are going to see a proof in just a moment that the real numbers are equinumerous to R2 by using Theorem 832. And so as a reminder from the historical lecture on set theory, Cantor proved that the real numbers were equinumerous to R2 in 1873, and this is where that famous quote, "I see it, but I don't believe it," because the original proof that Cantor gave was rather involved and technical, and so he was not sure if it was completely precise and rigorous, and he wrote to Dedekind to ask him if he could check his proof. Now, Dedekind and Cantor were friends and corresponded with each other. So Cantor conjectured this statement in 1887, and Dedekind, soon after hearing about it, gave a proof. But he did not publish nor tell anyone that he had a proof. And in fact, it was not until 1908 that Zermelo, browsing through Dedekind's old writings, realized that Dedekind had proved the Cantor-Schroeder theorem back in July of 1887. But this was not until 1908. And so Dedekind did not prove the result, which is out of character. Dedekind was published almost all of his results. But in the case of set theory, as we have noted, the general reception from mathematicians of the time was not in favor of Cantor's statements. And so Dedekind may have opted to just not publish and just keep his results on infinite sets to himself out of fear of how the math community will react to him in the same way that it had reacted to Cantor. And so Dedekind proves the theorem, 1887. But it's not until 1895 that Cantor finally figures out how to prove the theorem. And technically, he has a full proof. I wrote here partial proof, but Cantor did not believe he had a proof. His proof relied on a certain statement that he was unable to prove. And as we will see on Wednesday, this is the famed axiom of choice. It's an axiom. And so Cantor had been trying to prove this statement when in fact it cannot be proven directly from the axioms of set theory, and so it must be taken as an axiom itself. And so today, in the axiomatic system for set theory, we have that the axiom of choice is one of the axioms. So technically, Cantor did prove the Cantor-Schroeder-Bernstein theorem. Now, fast forward 2 years later, Bernstein was able to prove the theorem without relying on this axiom of choice. And so Bernstein gets the credit for the first publication of the theorem. And soon after Bernstein proved the theorem, he went to visit Dedekind, discussed the proof with Dedekind, and soon after, Dedekind found another proof that was independent of his previous one, and also independent of that of Bernstein and Cantor's, but again, did not publish. And so Dedekind, by 1897, had two proofs of this theorem that were completely different to those given by Cantor and Bernstein. And finally, we have 1898, when Schroeder published a proof of the theorem, which was then found to be incorrect in 1902. So before we get into the proof of the Cantor-Bernstein theorem, what we are going to do is prove Cantor's result from 1873 that the real numbers are equinumerous to R2. Now, Cantor in fact proved that the real numbers are equinumerous to Rn for any positive integer n. Now, once we prove this, we get via a simple induction argument that the real numbers are equinumerous to Rn. So how do we use the Cantor-Bernstein theorem to prove that the real numbers are equinumerous to R2? Well, what we need to do is show that R2 dominates the real numbers and that R dominates R2. So what does that entail? And so let's do some scratch work. So we need to show that the real numbers, so R2 dominates the real numbers, but this here, by definition, is equivalent to the existence of a one-to-one function going from the real numbers to R2. So equivalent to the existence of some function f going from the real numbers to R2 such that f is injective. That is one-to-one. And we also need to do that R2 is dominated by the real numbers. And so that is the existence of some function g such that R2 maps to the real numbers such that g is one-to-one. Now one of these we get for free because in this case we have a natural injective function. We can take our function f going from the real numbers to R2 to be defined by f of x is mapped to x comma 0. And just like that, we have our function. We essentially map the real line to the x-axis in R2. And this is going to be a one-to-one function. So what we really need to do is find a one-to-one function from R2 to the real numbers. But what we are going to do instead is not focus on the real numbers, but use one of the exercises from the homework. So from exercise 8.1.3, we know that the real numbers are equinumerous to the interval 0, 1, close bracket. And so what we are going to do instead, I'm going to go ahead and label this interval I. And so what we are going to show instead is that there is some function f going from, let's just switch to g. We have some function g from the Cartesian product of I with itself mapping back to I such that g is one-to-one. And now by theorem A12, we get that the Cartesian product of I with I is equinumerous to R2. And so this is essentially what we need to do, is find the existence of such a function g. And if we find the existence of this one-to-one function, then the Cantor-Bernstein theorem tells us that I is equinumerous to the Cartesian product of I with itself, and consequently we deduce that R2 is equinumerous to the real numbers. And so let's go ahead and prove this result. And what I am going to do is start the formal proof and then do some scratch work to explain the function g that we are going to define, since its definition is rather technical in terms of the decimal expansions being just being set up in the right exact way so that the function is an injective function. So let us go ahead and prove the corollary. I've modified it from how it looked previously. Now we have I is the interval 0, 1, close bracket. And then we want to prove that I is equinumerous to the Cartesian product of I with itself. So first we're going to take a function f defined from I to the Cartesian product of I with itself, defined by f of x equals the ordered pair x, 0. This is going to be a one-to-one function, because if we take f of x equals to f of y, that's the same as the ordered pair x, 0 equals the ordered pair y, 0, which in turn tells us that x equals y. And thus, we get that f is a one-to-one function. Now we're going to take an x in I, and this is going to be a number between 0 and 1, not including 0, but including 1. And so we have it. Let's look at the decimal expansion of x. And so we're going to make the following convention. If the decimal expansion of x ends in infinitely many zeros, then we're going to replace x with the decimal expansion which has infinitely many 9s. So what does this mean? So if we take x to be, say, 1/2, this is, as a decimal expansion, 0.5, but reality is that that's just infinitely many zeros repeating. We don't want to consider these types of decimal expansions for the function that we are about to create, going from I cross I to I. And so instead, we are going to replace the decimal expansion 0.5, infinitely many zeros repeating, with the one where we have infinitely many 9s, namely 0.4, and then we have infinitely many 9s repeating. And so this is the decimal expansion that we are going to choose. And so the function that we are going to do is going to be cleverly defined so that it is a one-to-one function. But before we get to the actual function, I want to mention sort of like the idea and intuition of what is happening and some of the things that fail if we are not careful. So let's go ahead and consider, so now I'm just going to do scratch work. And then we'll return to the formal proof after we have an idea of what the function should be. So we're trying to define a one-to-one function going from I cross I to I. And so this here, we're going to have inputs x, y, and we're going to get back a z. So one first thought when trying to define such a function in terms of the decimal expansion is if x was equal to 0 point, and then the 10th digit was x1, the 100th digit was x2, the 1000th digit was x3, x4, and then we just continue on in this way. And then y was also equal to then 0.y1, y2, y3, y4, y5. And so here, of course, these are the digits. And so we have that each xi and yi is between 0 and 9. So now we can go ahead and write g of x, y to be the decimal expansion x1, y1, x2, y2, x3, y3. And it turns out this function is going to be one-to-one. But now what I want to do before we get into the rigor is explain why this is absolutely necessary. We really do need to have this convention that we are writing numbers in terms of the expansions as infinitely many 9s, although you could also choose it to be infinitely many zeros, but you have to stick to the convention you choose, because if you don't, we don't have a function. Let me demonstrate. What if we took g of 0.5? And so we did not take the convention. And let's say that we had 0.51111, and then we just had infinitely many 1s. According to our definition, this is going to go to 0.5, and then we're going to go to 1 for the y, for the first digit in y. Then we're going to circle back to the second digit of x, which is now 0, since we're going to have infinitely many zeros. And so we're going to have this expansion. But if we instead took 0.5 as 499, and these are the same numbers, and now infinitely many 9s repeating, and we still took infinitely many 1s as our y, now our output is going to be 4, then 1, then 9, then 1, then back to 9, then 1. And these, of course, are not equal. But we are in trouble now, because our input x, y is the same as this x, y, since 0.5 is the same as 0.499, and so forth. And so we do need to have our choice of numbers to be in this way. And so let's go ahead and now return to the rigorous argument and prove that this function g is in fact one-to-one. Returning to the formal proof, what we are going to do now is with the convention that we have, we're writing numbers with infinitely many 9s repeating instead of infinitely many zeros. we're going to write for z and I, we're going to write it as z is equal to 0.z1, z2, z3, where each z sub j is the jth digit in the decimal expansion of z. Now, define the function g from the Cartesian product of I with itself to I by g of x comma y goes to the decimal expansion 0.x1, y1, x2, y2, x3, y3. And we claim that g is a one-to-one function. So what we are going to do now is take x, so we're going to show that if we take two distinct elements in the Cartesian product of I with I, that they map to distinct elements in under G, that they're mapped to distinct elements under G. So suppose x comma y and x prime comma y prime in the Cartesian product of I with I are distinct elements. So in other words, all we are saying here is that x comma y does not equal x prime comma y prime. Well, if they're not equal, that means that x does not equal x prime, or y does not equal y prime. So we can do a relabeling, and so without loss of generality, we may assume that x does not equal x prime. And the idea here is, if it happened to be that y does not equal y prime, we can just switch, we can choose our distinct elements differently. We could have chosen y comma x, and then y prime comma x prime. And under that labeling, now the x's and x prime are not equal to each other. And so that's how the without loss of generality is being used here. So we may assume that x is not equal to x prime. And what does that mean? That tells us that when we compare their decimal expansions, there is a digit for both of them that are not equal. So then, there is a positive integer j such that the jth digit of x does not equal the jth digit of x prime. Consequently, we have that if we take g of x comma y, we're going to have 0.x1, y1, x2, y2, and then somewhere along the way we're going to have x sub j, y sub j, and so on and so forth. But now this is not going to be equal to x1 prime, 0.x1 prime, y1 prime, x2 prime, y2 prime, and now somewhere along the way we have xj prime and yj prime. And now both of these are not equal since they don't have the jth digit being the same. And here we are using the convention, because by choosing this convention that we're writing numbers as infinitely many nines as opposed to infinitely many zeros, we are guaranteed that every real number between 0 and 1 has exactly one decimal representation of that form. And so, since we have that the two digits xj prime and xj are not the same, that forces these to not be equal, and thus g of x comma y does not equal g of x prime comma y prime, which tells us now that g is a one-to-one function, which shows that g is a one-to-one function. But since g is a one-to-one function, and it goes from the Cartesian product of I with I to I, we get that I dominates the Cartesian product of I with I, since by definition, we have that if a and b are sets, and we have a function from a to b that is one-to-one, then b dominates a. And so therefore, we get that I dominates the Cartesian product of I with I. But at the start of the proof, we considered the injective function for I to the Cartesian product of I with I. So we also showed that I cross I dominates I. So now we have both of these statements, that I cross I dominates I, and I dominates I cross I. And now Theorem 832 comes in and tells us that I cross I is equinumerous to I. So by Theorem 832, we conclude that I cross I is equinumerous to I, and that finishes the proof. We have now shown that I is equinumerous to I cross I. And now we get the statement that the real numbers are equinumerous to R2. Since by exercise 813, we know that I is equinumerous to the real numbers. Consequently, by theorem 812, which tells us that if we have two sets that are equinumerous A and B, and two sets that are equinumerous C and D, then the Cartesian product of A with C is equinumerous to the Cartesian product of B with D. And thus, we get that the real numbers Cartesian product with themselves is equinumerous to I cross I. Now we use the corollary that we just proved, along with theorem 813, which is how equinumerosity behaves like an equivalence relation. We conclude that the real numbers Cartesian product with themselves is equinumerous to the real numbers. And we have proven Cantor's theorem from 1873. Well, in the case when n is equal to 2, but the general case, which is for each positive integer n, the real numbers are equinumerous to Rn. I leave it to you to prove this via induction. So now we have settled this theorem of Cantor's, but as part of the homework for next week, you will be able to give another proof of the real numbers being equinumerous to R2, namely in exercise 8.3, number 12. So now we are going to transition towards proving the Cantor-Bernstein theorem. The proof that I am going to do is similar to the one done in the textbook, but I am going to be introducing terminology and notation that is not in the text. So namely the notion of what it means to be an ancestor. And so this is terminology that I am borrowing from my colleague Diana, but it does make the argument for the proof easier and more intuitive to grasp, as there are many moving parts to be able to conclude the Cantor-Bernstein theorem. But once we understand the notion of ancestors, we can go ahead, define a function that will prove the desired equinumerosity in the Cantor-Bernstein theorem. So let's go through and see what the notion of ancestors is. So first thing is the definition assumes the statement of Cantor-Bernstein. So the statement tells us that A and B we have some sets A and B, and we have that A is dominated by B and A dominates B. Now, if B dominates A, that tells us that there is a one-to-one function from A to B. And so in other words, the image of A is a subset of B that is equinumerous to A. So in the definition, we're taking A and B to be sets, and we are taking the following into account, that A is equinumerous to some subset B prime of B. And so in the language of Cantor-Bernstein, this here would be the B prime would be the image of A under some injective function from A to B. And similarly, we have that B is equinumerous to A prime, where A prime is a subset of A. Now we are going to go ahead and take F from A to B prime and G from B to A prime to be the corresponding bijections that we get from the assumption that A is equinumerous to B prime and B is equinumerous to A prime, respectively. For X in A, we will say that X has no ancestors with respect, and I'm going to abbreviate with respect to as WRT going forward. And so we say that x in A has no ancestors with respect to f and g if x is not in A prime. Now, if x has an ancestor with respect to f and g, that is, x is in A prime, we define the nth ancestor of x with respect to f and g for a positive integer n to be as follows. The first ancestor would be g inverse of x. The second ancestor will be f inverse, then g inverse of x, if g inverse of x is in B prime. And so this is crucial. So we define the second ancestor only when g inverse of x is in B prime. Okay, the third ancestor will be g inverse of f inverse of g inverse of x, when f inverse of g inverse of x is in A prime. And then we just continue in this manner. We can define the fourth ancestor in this way, the fifth ancestor, the sixth ancestor, so on and so forth. To better grasp what this notion of ancestor means, let us do a picture that will allow us to visualize what is actually happening. So here's a visualization. We have our set A, and I'm taking the part that is shaded in yellow to be A prime. So A prime is this here, and it's a subset of A. Over here we have B, and similarly, we have that B prime is the part that here is that's shaded in, and that's a subset of B. By assumption, f and g are bijective functions, and so f goes from A to B prime, g goes from B to A prime. But because f is bijective, that means that f inverse is a function. But specifically, f inverse goes from B prime to A. And in the same manner, g inverse goes from A prime to B. And now what we are going to do is visualize what does it mean to be an ancestor of x. So let us suppose that x has an ancestor. So if x has an ancestor, that means that x is in A prime. So x is going to be in here. So x is in A prime. Now, the definition tells us that the first ancestor of x is going to be g inverse of x. What does this mean? Well, we have our function g, but the function g is going from B to A prime. And because it's going from B to A prime, and g is bijective, that means it's onto. So we know that there is an element in B that maps to x. And so we have two possibilities. Possibility one, we could have that g inverse of x is inside B prime. But we also have a second possibility. So I'm going to change the color here. We also have that it could be not in B. And so I'm going to treat both of these cases differently. And so let us first assume that g inverse of x is not in B prime. And so we have g inverse of x, it's over here. So in this situation, we have that g inverse of x is not in B prime, and now it doesn't have a second ancestor. Because in order to have a second ancestor, we need g inverse of x to be in B prime. So in this case, we say, so in this example, x has exactly one ancestor. So let us continue. In the second possibility, we would have had that g inverse of x would have been inside B prime. And so now we have our g inverse of x is in here. And now we satisfy the condition to have a second ancestor for x. And the second ancestor is defined as f inverse of g inverse of x. F inverse is a function from B prime to A. And so, because we are in B prime, we can take we can take F inverse of G inverse. And so F inverse is going to map us to A. So we have two possibilities when we take F inverse of G inverse. Either we are in A prime, or we are in A minus A prime. So as before, we're going to consider these two cases separately. If we happen to be not in A prime when we take F inverse, so here is F inverse of G inverse of X, then we would say that X has, so in this example, X has exactly two ancestors. Since we don't satisfy the condition of what it means to have a third ancestor, namely that F inverse of G inverse of X is in A prime. And so in this case, we are not in A prime. So now let us consider the case where we are in A prime. So now we are in the example where F inverse of G inverse of X is in A prime. And now we can consider the third ancestor, since now we have that this is satisfied. So now we're going to take G inverse of this. But if we take G inverse of this here, as before, G inverse is a function from A prime to B. So once again, we have two possibilities. We can be in either of these. And so let's go ahead and consider when we are not in B prime. So in that case, we would have G inverse and then of F inverse of G inverse of X. And so that will be our element here, and it's not in B prime. And so consequently, we don't have a fourth ancestor because we don't satisfy that G inverse of F inverse of G inverse of X is inside B prime. And so we have that there are exactly three ancestors. So in this example, X has exactly three ancestors. And we can just continue. Then if we happen to be inside B prime, then we will have G inverse F inverse of G inverse of X. And then we can go ahead, take F inverse, since now we are in B prime, so we can take F inverse which maps us into A, and we once again have two possibilities. And we always have two possibilities. We are going to be either in A prime or not in A, or when we're going in the opposite direction, where via F inverse, we're going to have either we are in B prime or not B prime. But now we can do the same process again. We now take F inverse of this, and we have the two options. We are either in A prime or not in A prime. And if we are not in A prime, then we will have exactly four ancestors. If we are in A prime, then we continue. And the idea is, this either terminates, or we also have the possibility that there are infinitely many ancestors for the given X. And that leads us to the following lemma. So the lemma has the same structure as the definition. So we have A and B are sets, such that A is equinumerous to B prime, where B prime is a subset of B. B is equinumerous to A prime, where A prime is a subset of A. We have our corresponding bijective functions, F from A to B prime, G from B to A prime, and we can define the following sets, A0, A1, and A2. A0 is defined as those X's and A's such that X has an even number of ancestors with respect to F and G. A1 is defined as those X's such that X has an odd number of ancestors with respect to F and G. And finally, we have A sub 2, where A sub 2 is the set of X's such that there are infinitely many ancestors of X with respect to F and G. So in the case of infinitely many, what we will have is this dance, where we take G inverse of X, we are here. Then we take F inverse of this here, and we're back here. Then we take G inverse again, we're back here. And then we take F inverse again, so we're going to land in A prime. Then we're going to take G inverse and we land back in B prime. Then we take F inverse again and we land back in A prime. And this continues ad infinitum. And so that's the notion of ancestry. But what we are doing is essentially partitioning A. And that's what the lemma is telling us, is that A is equal to the union of A1, of A0, A1, and A2, and each of the AJs are pairwise disjoint. I said the word partition, but that's not entirely correct. It could happen that one of these sets is empty. And if that happens, we fail to be a partition because one of the conditions of a partition is that all the elements in the family of sets are non-empty. And so almost a partition, not quite, because we may have that one of these is empty, but what is the good thing that we do have is that A is equal to the union of these three, and each of the A sub j's are pairwise disjoint. Now the proof of this is not bad, and the idea here is each of the AJs is a subset of A. So proof, we observe that each A sub j is a subset of A, and thus the union from 1 to 3 of A sub j is a subset of A. Next, suppose that X is an A. Then if X does not have an ancestor, with respect to F and G, then X is an A0. Because we are interpreting in this situation, if it has no ancestors, it has 0 ancestors, and 0 is even. So we're going to have that X is an A sub 0. If X has an ancestor, then X is going to be in one of these sets in the union from 0 to 2. Oh, and I just noticed there's a small typo in the lemma statement. This should be from 0 to 2, not 1 to 3. I apologize. So X is in the union of the A sub j's, and thus A is equal to the union from j is equal to 0 to 2 of the A sub j's. And all that remains to show is that the A sub j's are pairwise disjoint. But the construction of the A sub j's, the definition of these, that we have even number of ancestors, odd number of ancestors, or infinitely many, that right there forces each of these to be pairwise disjoint. And so we can conclude, that we note that the A sub j's are pairwise disjoint by their definition. And so that finishes the proof of the lemma. And now we have all the ingredients necessary to prove the Cantor-Bernstein theorem. Because what we are going to do is use this lemma in two different ways. Because we could also do the situation where we have ancestors with respect to G and F, in which case our elements would be in the set B. So let's go ahead and prove the Cantor-Bernstein theorem. So let us now prove the Cantor-Bernstein theorem. So by assumption, we have that B dominates A and A dominates B. The definition then tells us that there exists injective functions, that is, one-to-one functions, f hat going from A to B, and g hat going from B to A. Now what we are going to do is set this up so that we can use the notion of ancestors. And so we're going to go ahead and define the image of A under f hat to be equal to B prime, and the image of B under g hat to be equal to A prime. Then that gives us the function f going from A to B prime, and the function going from g, from b to a prime, defined by f of a equals f hat of a, and g of b equals g hat of b, respectively. And both of these functions are bijective by construction, because both f and g are defined in terms of f hat and g hat. So we continue to be one-to-one because f hat and g hat are. But then we are onto, because f goes from a to b prime. But the way we define b prime is as the image of a under f hat. So f is going to be onto b prime. And similarly, g is going to be onto a prime, since a prime is defined as the image of b under g hat. So we are now back in the setting of what we were just covering with the notion of ancestors. We have our set A, we have our set B, we have our bijections from A to some subset B prime of B, and we have a bijection from B to A prime, where A prime is a subset of A. The next thing we are going to do is bring in the notion of ancestors, but to both A and B. And so this is where it differs from what we did. So what we have is that A0, A1, and A2 are as we defined them earlier, but there's nothing special about the notion of ancestors being defined to A. We could do it to B as well. And so we can define what it means for an x in B to have an ancestor. And so we have B sub 0 is the set of x's and b's, such that x has an even number of ancestors with respect to g and f. And now I flip the order to emphasize that when we go back to the notion of ancestors, all that we are doing is replacing all the symbols and just flipping them over. So here in the lemma, we would have, instead of A, we will have B, and then B will be A, and then we replace here A with B, B prime becomes A prime, subset of A, and we continue through, and now the same statement holds. And so we have a way that we can define B0, B1, B2, and now the lemma continues to hold. And now what we want to do is investigate how f and g behave on A0, A1, A2, B0, B1, B2. So here's our example that we did earlier, where we had an element x in A, such that x had exactly 2 ancestors. So now this x is in what we are calling A sub 0. Now, what we want to investigate is, how does this compare with the sets that we have done for B, B0, B1, and B2? So here's how. Well, we're going to take x and we're going to apply f to it. So that's going to give us an element over in B. But from the way we've constructed things, we know that f is a function from A to B prime. So that's going to give us some f of x. That's going to be in B prime. So let's say that this here is f of x. And what I'm going to do now is call f of x equal to y. So now, when we think about this from the perspective of B, and we say, how many ancestors does y have with respect to g and f? Well, the first ancestor of y is going to be f inverse of y. Because what we are going to do now is just flip every appearance of g with f. And similarly, every appearing of f with g. And so we take f inverse of y. But f is a bijective function. So f inverse of y gives us back x. And so that's the first ancestor of y. Now we go as before, and we are going to take g inverse of f inverse of y, and doing so is going to give us g inverse of x, since f inverse of y is x. And so now we got that g inverse of x is going to be g inverse of f inverse of x, of y. And so now this is our second ancestor. And now we go ahead and we take f inverse of this to find the third ancestor. And so we take the f inverse of this, and we're going to get f inverse g inverse of x. And so this here is going to be f inverse g inverse of f inverse of y. But we can't continue this process any further. And so what we get is that y has exactly 3 ancestors. But you can see from here that x had 4 ancestors. The process would show that then the corresponding y would have 5 ancestors. And so what f is doing when we send everything to b, we are essentially adding one more ancestor to the x we had in the case when we have an even number of ancestors. But the same holds true if we did this in the case where we had an odd number of ancestors. Because, as before, we take x and we apply f to it. So then f of x is going to be in b prime. And so let's say that this here is f of x. And now we're just going to call this y. Then we take f inverse, and we get that f inverse of y is x, and that's our first ancestor. But then we apply g inverse, and then taking g inverse of x gives us our second ancestor. We take f inverse of g inverse, and now we have our third ancestor. And then we take g inverse once more, and we have our fourth ancestor. But now this here is not in b prime, so we have exactly 4 ancestors to y. So the examples we just did show that if we take an element of a0, so it has an even number of ancestors with respect to f and g, then when we take f, the elements of f of a0 will have an odd number of ancestors. And so the claim is that this here is in fact f of a0. But the logic that I'm explaining seems to suggest that if we take f of a1, that should be equal to b0, and that is not the case. The reason is that if we chose an x in b0 such that x has no ancestors, with respect to g and f, then by definition of ancestors, this implies that this x is not in b prime. But the image of a1 has to lie inside of b prime because f is a function going from a to b prime. And so we don't have that equality. So we will show that b1 is equal to f of a0, but we need to be careful with a1 and b0. But now a2 does map to b2, and so that's going to be true. And so this here b2 is going to be f of a2. And so what we need is what to do about b0. And so what we are going to do is trick this into satisfying what we want. And so what we are going to do, since g is a function going from all of b to a prime, and every single element in a1, since it has at least one ancestor, we know that it lives inside a prime, then we can show that b0 is equal to the inverse image of a1. And so that's what we are going to claim. So here's the claim. F of a0 is equal to b1, f of a2 is equal to b2, and g inverse of a1 is equal to b1. Now, I am not going to prove this today since the video is already running long. And so what I will do at the start of the next video is prove this statement here and discuss how that same proof strategy will show that these here also are equalities. And so for now, we're going to assume this. So we now assume the claim. And now we use the following. Since f and g inverse are bijective functions, we have that a0 is equinumerous to b1, a2 is equinumerous to b2, and a1 is equinumerous to b1. And now what we are going to do is define, finally, a function that is bijective from a to b to prove the theorem. So lastly, let h from a to b be defined by, and we're going to take h of x, and h of x is going to map to f of x if x is in a0 or a2, and it will map to a g inverse of x if x is in a1. And by the way we have constructed this function is going to be bijective. So we now show that h is bijective. So I'm going to go ahead and show that h is onto, and I leave it to you to verify that h is injective. So to this end, let's go ahead and let b be in b. By the previous lemma, b is going to be in some b sub j for some j equals to 0, 1, or 2. Now, if b lowercase b, if b happened to be in b1 or b2, then we have that f maps to it. So let's go ahead and do that. So if b is in b1 union b2, then there is an a in a0 union a2, because the image of a0 under f is b1, the image of a2 under f is b2. And so if we had, so as a consequence, we get that there's an a in a0 union a2 such that b is equal to f of a, but by definition, that is h of a. And so we got that. And so it remains to consider what happens when b is in capital B sub 0. Now, if b were in b0, then there is a lowercase a, but now it's going to be in a1. And so we're going to be taking g inverse. And so a1 such that g inverse of a is equal to b. But g inverse of a, since a is in a1, that is our definition for h of a. Thus, h is onto. As an exercise, show that h is 1-to-1. And once you show that, we are done with the proof. So therefore, H is bijective, which shows that A is equinumerous to B, and that finishes it off for the Cantor-Bernstein theorem. And so this notion of ancestry was the key aspect for making the proof work, because it allows us to essentially partition A and B, although I am using the word here incorrectly, since again, there is no guarantee that each of the sets are non-empty. And so that finishes it off for today. I owe you a part of the proof at the beginning of our next video, namely that we do have these equalities here. And so we'll discuss this in the next lesson, and we will also be proving that the power set of the positive integers is equinumerous to the real numbers.